So it gives me great pleasure tonight to bring to the stage Marlon Dutra, one of my best friends. He's originally from Brazil. Now he's a network engineer, production engineer for Facebook out in Menlo Park. And he's going to be talking tonight about hardware security modules. Yes, Yubikeys and all those kinds of things. So I will turn it over to Marlon now.
Okay, thanks. All right, let's just see. So yeah, good evening, and just get my.
Is that good?
Good. All right, let's get started. So yeah, just a little bit about myself. So I've been working with as a NetSec, sysadmin, whatever it takes, since like 1995 in Brazil, and then I moved to. So I started working at Facebook in 2012. That's when I moved to the US, and I'm a tech lead there in infrastructure security. So I work on a lot of different projects, and one of the biggest projects that I've been working lately is around HSMs and crypto devices, and so I want to talk a little bit about that, what those devices are and what they do, and etc. And so I've been pretty busy with that stuff. And my team owns several crypto services like our certificate authority, authentication services, and authorization, and etc. Pretty much most of the frameworks that all our backend services use as to do security is somehow managed by our security teams. And we also own the entire SSH infrastructure to Facebook. So we have SSH running, hundreds of thousands of machines like everywhere in the world. This is my fourth time here. So the first time was like 10 years ago, and I was talking about an LTSP case that we had in Brazil. And then the last three times I was already living in the US. So first time I talked about Facebook, our load balancing infrastructure. So before security, I used to work as a network engineer in the networking team. I was responsible for one of our layer of load balancers. And I came here to talk about that. Last time I talked about SSH. And this talk here is not about SSH, but it's about some primitive cryptography stuff that SSH uses as well.
Marlon, according to this timeline, your next talk should be in 2020.
Yeah, I think I'm establishing a pattern that I'll probably have to be here every 2 years. Yeah, exactly. that's true. Yeah, that's true. I'll probably be working the same thing next year. So let's wait until I'm busy with something else that's interesting. So yeah, I'm going to talk about crypto devices. Those things are pretty old. There's nothing new about them, but unfortunately, they're not as famous as I wish they were. So it's more common like in enterprises and corporations that people use this kind of stuff. It's not so common everywhere else, even though they are actually pretty cheap, and they've been becoming cheaper and cheaper over time. So today, it is possible for us to have some of these devices for like $40 or something like that. And the prices can go up like a lot for thousands. I'll show some pictures with some devices that can cost like tens of thousands. And another unfortunate thing about these devices is that there's no like a standard name for them. So each manufacturer will use like a different name. So you can hear about them for like HSMs, which is very common for the larger stuff, like hardware security modules. PAV, that's pretty common. TPM, usually when those devices are part of your computer, like a solder in the main board, those are called TPMs. Smart card, that's another name which is pretty common. Secure enclave, Apple started using that name. Token or crypto token or etc. And I'm pretty sure that if I start seeing some other implementations, people will come up with like different names. But essentially they are all the same thing. They all provide the same functionality. And the number of functions might vary from manufacturer to manufacturer, but essentially I think the basic functionalities will be basically the ability of like having private keys in hardware, like in the device, and exposing operations. So in such a way that the private key itself will never be exposed. So they usually have ability to generate the keys in the device itself. That's one of the most important functionalities. So that key has never ever existed anywhere else. So you can tell the device, please device, generate a key for me. and I want the key to be an RSA 2048 or ECC or EAS, whatever the key supports. So when you buy the device, there is usually a list of keys that the device supports. And so that key is created inside the device itself. So the device has a random entropy mechanism that it creates like random bits. And that key would never be exposed anywhere. That's the safest thing to do. Because if you create the other thing that you can do, you can create the key in your OS, and then you can port the key to the device. That's not very smart, because that key has existed somewhere else. And if your OS is compromised or you have anything, anyway, that key could be stolen. And the whole point of this, using these devices, is that key cannot be duplicated. Like once the device is fused in hardware, it's virtually impossible to duplicate that key. I wouldn't say impossible. I would say just the bar is very, very high, to the point that it would become interesting for an attacker. It's very difficult to expose the key. So once you have the key there, the key is only useful if the device allows you to do something with it. So the most common operations on these devices would be decryption and signature. If you have an asymmetric key, and I'll talk a little bit about asymmetric keys in a second. Some devices, they will support encryption and verification as well, which might not be very useful because you can do that with the public key. And most of these devices, they support random number generators, they support HMAC and some other like functions that you may need, like key derivation or key negotiation, etc. But the most basic thing, and I'll show that in a sec, is decryption and then signature. Most of them support multiple ciphers, at least asymmetric ciphers. I think the most common these days would be RSA. RSA 2048 is probably the standard these days for certificate and etc. And they also support DSA keys, which are only useful for signatures. So it's really common that people are using like elliptic curve for cryptography, which is really good, it's super fast, but you can only do signatures with those. So if you need to do decryption, you have to use RSA. Unless you use key derivation, which is outside the scope of this talk. In most of these devices, they support some sort of authentication. So in most of the cases, we really don't want people to get your device and start using your keys. So you can authenticate to the device somehow. It would be either a PIN or a smart card or quorum if you have secret sharing, so you can get a secret and you can share that secret and establish a quorum. Something like 3 out of 10 people have to be present so I can use that key or something like that. So this is possible. Some devices support that. So before I go further, a little bit of asymmetric crypto if you're not very familiar with that. So symmetric crypto, that's very straightforward. Like you generate a key, that key is just a sequence of random bytes. Like there's nothing special about the key. You just cat dev you random, you generate a key. That's symmetric key, and you use that key for everything. Encryption, decryption, verification, signature, for everything you use the same key. This is good for a lot of stuff, but it's not very good for security and for identification. That's where asymmetric crypto is really interesting, because you have a key pair. So you have the private key, that private key, you can run a derivation function that will expose the public key, and then you can use the public key for encryption and verification. And then you can use the private key for signature and decryption. And so that's really interesting. So you can have private keys living in those token devices, and you can expose the public key whatever you want, because they're public. So there's nothing special about that. So this is really useful in the certificate chain. So if you have like a PKI, a public key infrastructure, so you have a private key, and you can generate a certificate request that's basically the public key signed by the private key. And then you can send this to a CA. The CA will authenticate you somehow, and then the CA will give you back a certificate. Certificate is basically your own public key signed by the CA's private key, and that's where the certificate is. And the public key component, that's pretty public. Certificates are public. Like you can query any certificate of any website out there, even though the private key has never been exposed anywhere. So this is a very complex topic, of course. Like this Wikipedia article is very interesting if you want to read a little bit more about asymmetric crypto. And most of the things that I'll talk through the rest of the talk is about asymmetric crypto. Shapes, so those cards, there's like several different form factors. The one that I'm using here now is a USB-C. It's almost invisible. That's the top right one. That's the one they have here. They have USB-C, USB-A. There's several manufacturers. The one that I'm using here is from Yubikey. They are called Yubikeys. And at Facebook, you use Thales a lot. So Thales is one of the biggest the biggest manufacturers of HSM. It's a French group. And yeah, there's several ones. Like there's smart cards, like your debit card and your credit card, if it has a chip, it is actually a token device. So when you use your debit card, basically what's happening there, so your debit card, if it has a chip, it has a private key there, and the bank has the public key associated with your account. So when you insert your smart card to the ATM, so the bank sends a challenge to the ATM, and the ATM asks your smart card to sign that challenge with the private key inside the card, and then you send back the response to the bank servers, and the bank will authenticate, wow, this is actually a card that we trust, and then it allows you to do whatever the operation that you want, like check your balance or or get cash, etc. So it's essentially the same thing. Like the primitives are exactly the same. They just present in a form of like a credit card. The prices vary a lot, so those small Yubikeys like you can find in Amazon for like 40, 50 bucks. And the big ones like the PCIe cards and the appliances, they range from $10,000 to $35,000 like each one. But those are the ones that are used at Facebook. They're pretty fast. Like so, those cards, we use those PCIe cards. They can do like 20,000 crypto operations per second, and which is pretty significant. This card that I'm using here, it's a little bit slower. It can do like 5 per second. So that's how different it is. And so yeah, if you really need like performance, you really need to have the big ones. And they also have a lot more features. They support symmetric crypto, which the small ones usually do not support. In terms of interfacing, on the software side, I'm going to talk quite a little bit about PKCS 11, and I'll tell you what it is in a second. So Microsoft have their own standard, and I think they have several generations. The latest one, if I'm not mistaken, it's a CNG, which is the Crypto API next generation or something like that. It's not PKCS compliant, but it's open, so if you develop software for Windows, that's like pretty standard. There's a lot of proprietary libraries, so whenever you buy those HSMs, token cards, they usually come with libraries, and then they expose the interface, and then you can dynamically link against the libraries and do whatever you want with it. So most people use PKCS 11 because it's the standard. Pretty much all vendors, they support that. Even Thales, if you buy an HSM from Thales, they are going to give you a PKCS 11 library. On the physical side, the small ones will be USB, like pretty standard USB-A, USB-C. PCIe, as I showed in the picture before, that's quite common if you want to have a high-performance HSM in your computer, so you don't want to talk via network to it. NFC, that's becoming more common, and it's basically the same as the USB, but it's useful for mobile devices. So if you have an application on your mobile device and you need to do some offload, you need to offload some private key operation, you can just touch it, the thing, and then it does the operation for you. Like it's usually like signing or decryption of like a small payload, so you can communicate in the NFC very, very quickly. So that's becoming more and more common over time. IP, of course, if you have an appliance, like the one that I showed before, like the big one at the bottom. So they communicate over IP, and then you establish trust basically by using cryptography. So those are very common in the payment industry. So all the banks and credit card operators, they usually use a specialized version of the appliance, and to sign all the banking operations. So if you have like if you need to send the bank like authorization for payments and etc., you have to sign that thing, and then you sign and you send to the bank, and the bank will authenticate you and actually proceed with the operation. One interesting thing that I didn't mention about the big ones is that they are tamper resistant. So they have all sorts of controls in the entire box. So if we start unscrewing it, it shuts itself down and erases all the keys. Yeah, so it's pretty much, I wouldn't say impossible, but it's very difficult to steal anything there. Like if it has like shake sensors and etc. So everything that you do, which it thinks that people are trying to tamper with that, you just erase everything. And the small ones don't have that. And so yeah, if you really want to get serious about that, the big ones are the way to go. They're just quite expensive. But I believe that if you need that, money will probably not be an issue. And in the grand scheme of things, it's really not that much.
Another way to test it out is send one of those boxes to Russia.
Yeah.
They can't crack it,
Yeah, a challenge response. Like, this is a challenge. Like, yeah, respond this challenge, and then, yeah, we're gonna believe the threat. Yeah, that's true. So a lot of companies we have like red teams that they basically do that. And when we finish a system or like a design or something, like, so the next step before they go to production, we send this whole design to the red team, and then we don't talk to them for the next several weeks. If they can break it, we can't launch it. And yeah, we have to do that, because sometimes we hire some external companies to do the same. Because yeah, you never know until someone actually really tries. PKCS 11, so as I said, it's a standard. So if you read at Wikipedia about it, that's pretty much what it says. It's just an interface. Like, what is an interface? It's like, think of a function. It's the functional signature. Like, the function has this name, and it receives these arguments, and it returns this kind of arguments. This is an interface. So that's what PKCS 11 is. So it basically says that if you want to be standard, you have to create your .so, your dynamic library, and your dynamic library has to export that interface. Like, your .h in C++ should look the same pretty much with any implementation. The .cpp will vary according to your own implementation, but the interface should be the same. And which is great. So like, you can do whatever you want with the implementation details, like, so, and that should survive over time. So now we're talking about USB and NFC and whatever. Like 10 years from now, God knows what's gonna happen, and but the interface will still be the same. So this has been around for many years. I'm gonna use a couple of tools. So this talk will be a little bit of slides and a little bit of like a demo. I'm not gonna type anything. I like basically copy and paste, and every command that I use here. There is one of the QR codes that I'm going to show through the end of these slides. It's basically a script file that I have in GitHub with all the commands that I used here. So just so you don't feel pressed to actually start taking note of everything. And most of my URLs will have QR code if you want to photograph them. So OpenSSC, that's an open source project, has been around for a while. It's basically a PKCS 11 toolset for Unix that works pretty well in macOS. In fact, here I'm using macOS, and I think they have support for Windows as well. We can use Visual Studio to build, and it supports like all sorts of like different devices, and it supports Yubikeys as well. So if you don't, you can use the software directly from Yubiko, but you don't need to. You can you can download OpenSSC, and that will have libraries for pretty much everything. Not only libraries, but like several tools to manipulate the devices, create keys, and etc. It has sets of libraries and OpenSSL engines that I'll talk a little bit more. OpenSSL, it's pretty much impossible to talk about any crypto-related topic without mentioning or showing something around OpenSSL. That's the most common tool in this field. OpenSSH, for the same reasons, like everybody uses that. And I'll use also the Yubiko PAV tool to manipulate the state of the device itself. Even though it's not strictly necessary, you can do that through OpenSSC if you want it. So obviously the Yubiko PAV tool only works with if you buy something from Yubiko. So if you buy a smart card from some other vendor, most likely that vendor will have their own tools as well. And most likely everything could be done with PKCS 11, which, as I said, pretty standard. So yeah, so from now on I'll basically talk about things around the Yubikey. So when I buy a Yubikey, it comes like, I would say empty. There's no keys on it. So it has the internal application that's like done by them. You can't change this, but the slots are empty. So all these devices, they have this concept of slots. So a slot basically is a place where you can have a key. This particular device that I'm going to use here has 4 slots, so I can have 4 different private keys on it. That's usually enough for user identification. Most of the times we just use one. I use only one myself. And some people might want to use different private keys for different things. That's fine, and that's the main reason those devices have more than one slot. If you have some professional application like an HSM, those HSMs, they will have a lot more slots. So Yubiko, for example, they have a small HSM which is USB, and they have 128 slots. And so those are useful. So if you have like multiple CAs, or you have like backup keys and etc. Or you may have keys that need to be different ciphers, like so I want an RSA key or a DSA key and etc. So you can use multiple slots to do that. So the small ones, most of the ones that I know, they have 2 or 4 slots. 2 slots is also pretty common. So what I'm doing here, so this first command, let's see if I have a mouse here. So yeah, this is basically like an initialization thing. Like it just sets a unique ID in the device. So the operating system knows if you have multiple devices, you can insert many devices into your machine. The operating system will know how to distinguish them. Most of these devices, the small ones, they are protected by PIN, which is a 6-digit number. So whenever you want to use the private key, you have to type your PIN. Pretty much the same as a debit card. And some devices, they will support alphanumeric pins. It's not very recommended because the PKCS 11, when it was written back in the day, a lot of the implementations only supported digits. So that's up to you. You might break something. There is this thing called PUC. So PUC is used when you need to change the pin. So if you forget the pin, you can use the PUC to change the pin. For me, it's kind of useless. And the Yubikeys have this thing that they call management key. So whenever you want to change the state of the thing itself, like generate a new key, importing a key, or importing a certificate, etc., you have to use this management key, which is a random thing. So just generate by reading the heavy random, and that's it. So yeah, I'm gonna switch here to a terminal. So can you guys read this? Yeah, it's good. So I have a key here inserted in my USB-C slot. It probably has a key on it, so I can use these commands here to reset the whole thing. So it's about reinitializing here. So now I have like a Yubikey that's empty. So this pretty much the state if I...
Please come to the information desk.
Is that us?
Please come to the information desk.
Yeah. So basically I'll copy and paste the commands that I showed in this slide, which are these ones here. So I'm not going to explain that later. Yeah, so the new ping, let's do 1, 2, 3, 1, 2, 3. And then the PUC, 1, 2, 3, 1, 2, 3, 1, 2.
What's the difference between a pin and a...
So the PUC has to be used if you forget your pin. So the idea of the PUC is that you write the PUC somewhere, in a password manager or something. In the pin you're supposed to remember. So if you forget the pin, you can use the PUC to get a new pin. If you forget the PUC, you're done. There's nothing that you can do about it. You have to erase the card. That's what I did now. If you erase the card, you lose your private key.
So I wouldn't be surprised if once in a while working, you hear over the cubicle a coworker suddenly say, "What the fuck?"
What the PUC? What the PUC? Yeah, I never need to use the PUC, but yeah, if you forget your PIN.
Are these the same devices that you would use like to link to your Google account? That
That's the U2F. So this particular device can do U2F as well. But that's a capability of this particular device. Not all smart cards can do U2F. Yeah, that's a good question. Yeah, some devices can do that. Yeah. But yes, you're right. This particular device can do that.
Is that management key something you need to save too? Or is that
Yes, you have to save because whenever, and I'm going to use that a couple times, whenever you need to change the state, yeah, if you want to write something to the device, you need the management key. And then I'm going to write. So actually I'm going to open a VI here and just paste the key because I'll need it. And so now, going back to so now my device is initialized. So it has a PIN, it has a management key, it doesn't have keys yet. So I can't use it for anything useful, but at least it's initialized. It kind of belongs to me. So the next big thing that you have to do when you buy this device, you have to create a key. So I have to ask the device, hey device, create a new key for me. So that's what this first command does. And so you have this, so the action, generate a key. As I said, you can also import a key. That's not very smart. I would only recommend doing that. So let's say that you have a certificate, like a public certificate signed by, I don't know, DigiCert or something like that. You pay like a lot of money for that. You still have like a year until it expires. You don't want to buy another one. So in that case, okay, import the private key to the device. But you have to keep in mind that that private key has existed somewhere else, and then it might have been compromised already, and you don't know. But in most of the cases, I would strongly suggest you to generate the key in the device. The -S here is the slot. So the 9C is the default slot that Yubikey suggests you to use it for whatever reason. So okay, we're going to use it. And then once I create the key, the device will give me the public key. Because as I said, the public key is public. And so the device will give me that. So let's basically do that. So yeah. So I need the management key because I'm changing the state of the device. So I'm asking the device to do something that will change its internal state. So let's just...
That's the management key, that one?
yeah, the long one. It has to be that long. So it's now blinking here and doing something. It's basically generating a new key, which is a lot of computational work to do it. So I have a new key. So if I look at my directory now, I have this public key. It's just a standard public key, nothing special about it. And that public key corresponds to the private key which is inside my device, which is invisible. There's absolutely no way that I could see that, and as far as I know. And so yeah, that's pretty much it. So a couple more things that we have to do. So now that we have a key, it's nice to have a certificate as well. There's a lot of, it's not like strictly necessary for some applications, but some other applications, they require that you have a certificate, either a public certificate signed by a CA that everybody trusts, or a self-signed certificate. Like in this particular case here, for this example, I don't have a CA to sign my certificate. So I'm going to create a self-signed certificate by basically using this command here. So what I'm doing here is, no, I don't want a dictionary. Oops. Oh, God. All right. So basically, I'm asking, so I have to verify the PIN because to create a signed certificate, I need a signature operation. So basically, I'm asking, like, verify my PIN. The next action will be self-signed certificate on that particular slot that I created the key. The subject of my certificate will have my own name. CN is common name. And I want the certificate to be valid for 10 years. And this is the public key. And it will output the certificate itself. So yeah, let's paste that. So the PIN, which is like 123, 123, boom, done. So let's get. So now I have the certificate and I have the public key that I had before. So if I look at the certificate here, X509, yeah. So this is a self-signed certificate. So the issuer and the subject are the same, which basically says that this is a self-signed certificate. The certificate is good for like 30 years. And then this is the public key of my certificate. So the public key is exactly the same public key that I have on that other file, publickey.pen. And so yeah. So now I can, yeah, this is the command that I type. I have this X509 alias, but it's basically OpenSSL, X509-text, whatever. And so I suggest you to have an alias because there's a lot of stuff to type. And so yeah, the next thing that I have to do, I have to import the certificate to the device, so the device can carry the certificate. I don't need to have the certificate in a file anywhere. I can, but I just don't need it. So these devices, they have the ability to import the certificate. I need the management key for that because I'm writing something to the device. So if I'm writing anything to the device, I need the management key to allow that operation. Oh, done. The interesting thing now that I have a certificate, if I go to the macOS keychain, I can go here and this is my certificate. So the operating system knows about these devices and they are always following what we're doing on the device. So the macOS keychain has exactly the certificate that I generate here, and everything in macOS that uses certificates and use the keychain for that, like Safari or Chrome or etc., will have access to this key. And then I can use this key as a client authentication to pretty much any website that supports TLS mutual authentication, which is pretty cool.
So the certificate is not actually in the key store, is it?
The certificate? No, it's not. It is in the device. Yeah, that's why I have this keychain here, like called PIV, which is personal identification.
Yeah, it's actually retrieving it from
yeah.
the device.
So if I pull the device now, this item here will just disappear immediately. Yeah.
Ah.
Yeah. Or if I have multiple inserter, like you'll see multiple entries there.
I like that.
That's very cool. And so in Windows, it's the same thing. Like if you plug a PKCS 11 device in Windows, it will just pop up in the keychain as well. Unfortunately, Linux does not have a keychain. So each browser or each client in Linux has to implement their own thing. All the famous browsers like Firefox and Chrome, they all support PKCS 11, so it would just work. But the bad part is that the browsers themselves have to implement the whole thing because Linux does not have that. It's a standard thing. So yeah, going back to the slides. So we have a key now. So my device is fully initialized. So I could say at this point that I'll never need the management key anymore. And of course, we should save this somewhere safe. But ideally, there's no reason for me to use this anymore, because unless I need another key for some other reason. So So now we can use it. Like say, let's use it to do something interesting. So as I said before, so this is an asymmetric key. It's an RSA 2048 key, which the default I could create a 4096. There's no reason to do that. It's much slower. It doesn't add much benefit. I mean, today, maybe 20 years from now, probably yes. But today, the 2048 is pretty good. And so this is an asymmetric key. I can only do two things with it, two very primitive operations with it. Signing, like signing small messages up to kind of 200 bytes or something, and decrypting small messages up to 200 bytes. It's usually up to the size of the key, which is 256 bytes. And so yeah, let's do that. So going back here, let's say testing encryption. So let's say that I have a message. Okay, I have my message. It's like 21 bytes, so that's enough. I can sign up to 200 and something bytes. And pay attention to what I'm doing here. Like, so I'm running this command here, and then I have my message encrypted. So I have the message.crypt. So this was the command that I ran. I didn't talk to the device at all, because encryption thing, all the encryption is done using the public key. There is no reason to use a private key to do encryption, unless you're using symmetric keys. If you're using symmetric keys, then yes, you need that only key to do anything. If you're doing asymmetric crypto, you only need the public key to do verification and encryption. And that's the reason that I just use OpenSSL. Very standard in the macOS or any box pretty much. Or you can use like any tool set that you want, like whatever supports RSA, you can use to encrypt anything. To test, to decrypt that, then I'm gonna have to use the device. So there's many ways to do this. So PKCS 11.2, that's probably the easiest one. So what I'm doing here, I'm asking the device to decrypt this message, and I'm telling the device this message was encrypted with RSA using the padding, the PKCS 1.5 padding. There's multiple padding algorithms. So I'm basically telling the device this message was encrypted that way, because the encryption blob has no metadata. So there is no, it's impossible to say how that message was encrypted. So if you look at the encryption here, yeah, it's basically garbage. There's no metadata at all here to say which cipher was used and etc. So I have to tell the device that. And so that's what I did here.
So you say you're talking to the device at that point?
Yes. Yeah.
So PKCS 11-tool.
It's a CLI around the PKCS 11 library.
For your default device? Or
if I only have one device, and that device has only one slot, it will use whatever it finds first. If I have multiple devices or multiple slots used in the device, I would have to tell the PKCS 11.2 with -s or something which slot to use, otherwise it would fail.
Can you list the devices?
Yes. There is a list slots, which are capital L. Yeah, so I only have that. So, yeah. So PIV2, card holder, blah, blah, blah. So if I have slot 0, because I'm only using one slot. So if I have more slots on the same device, it will show all of them. So that's the interesting thing in PKCS 11. If you only have one device and one key, you don't need to specify anything. It always finds your key. So let's do that. Oops, not this. Let's go back here and copy and paste it. Yeah. So this needs my PIN, because I'm using the private key, which is 123. I don't need this. Yeah, that's our message. So this came from the device itself. If I pull the device out, it's impossible to do it. And nobody in the world could possibly decrypt this message without this device and the PIN. And questions so far?
So you have a PIN for doing those kinds of operations, and you have a management key for...
Management key is when you change the state of the device. So when you are asking the device to sign or decrypt things, like you're not changing anything on the device. Yeah, it's a read-only operation for the device. If you want to change if you want to write to the device memory, you need the management key. That's something particular with this device. So there's nothing about PKCS 11 about that. So different devices will have different stories around this. For example, the Thales HSMs, the way we set them up, is that if I want to do any writing operation, I need to have a quorum over smart cards. So I need to have at least 3 or 4 people to establish quorum, and then the device will allow you to do anything with it. And it all depends on how you set this up. So the other thing that you can do is signing. So those are basically the 2 things that you can do with asymmetric keys. You can sign and you can decrypt. And everything else is kind of a derivation of that. So signing is the opposite. Like, so when you sign something, you need the private key to sign it. And then you can do the verification however you want with the public key. So in that particular example here, I'm using the same PKCS 11.2, using the -s, which is -- sign. And so I have to tell the device how I want the signature to be done. So I want a SHA-256. I don't use SHA-1 anymore because Google has proved that they found collisions there. So definitely use SHA-256 at least. It is an RSA key, so I have to use a -RSA. And the padding, I'm going to use PKCS as well. And -I is the message that I want to sign, and -O is the signature. So I'm basically telling, put the signature on this file. So let's do that. Just copy and paste here. Yeah, again, I need a pin. Yeah, this device has no context pin. Some devices have context pins, which is kind of annoying. This device doesn't have it, so I just hit enter. So now I have my message and I have the signature. One interesting thing about asymmetric keys is that the encryption blob and signatures, they're always, for RSA keys, they're always the exact same size of the key itself. So every signature in RSA will be 256 bytes if the cipher is 2048 bits. So if I read the signature, yeah, it's just basically random string of bytes. Nothing special, no metadata. It's impossible for anyone to tell this is a signature at all, because there's nothing special about it. To verify the signature, I only need the public key, so I don't even need to talk to the device. I can just use OpenSSL for that. So OpenSSL has this digest command. That's the command that does all sorts of like signature operations, signature verification, hashing, and etc. Yeah, so basically I'm telling as I said, the signature file does not have any metadata, so there is no possible way that OpenSSL will know how that message was signed. So I have to tell OpenSSL that. So basically I'm telling, hey, this was signed with like SHA-256. And this is the public key that I want to use to verify the signature. This is the signature file. This is the message. Verified OK. If I change the message, and I rerun the command, the verification fails. And that's the whole point about signature. Like the message and the signature must never be changed. And that's the whole point. Like you are verifying integrity. You're not verifying secrecy, you're verifying integrity. So nothing can change there.
Is there a size limit on the message?
Yes, there is a size limit. It's defined by the, well, yes and no. There is a size limit, which is the size of the key. But you never sign the actual message. You hash the message and you sign the hash. That's how all signatures in the world are done. And so I can sign like a huge file, but I'm not actually signing the file, because that would take like forever for the algorithm to compute that signature. So that's why you have to specify the hash, because it would actually sign the hash. So in this file, well, that's why you have to use a strong hash. And that's why I suggest you use a SHA-256. You can sign with SHA-1, that's fine. But if someone finds a collision, they can sign a different message that would produce the same signature. And that defeats the entire purpose of signatures. And Google has an article that they published last year where they proved they could have like a PDF file and an image producing the very same hash. So if you get those 2 files and you sign them with OpenSSL, for example, or whatever, they would produce the very same signature, even though they are completely different files. And so it's not a weakness on the signature algorithms. It's a weakness on the hashing algorithm. So all signatures, they involve like these 2 operations, like hashing, and so that's why you have to have like a strong hashing plus a strong cipher to sign the hash. So what actually got signed here is the, I think SHA-256 message. Oh no, how do I do SHA-256? No, SHA-SAN. Where is that the default? Oh, -A. Okay, -A. Yeah. So actually this was signed. not the message. So yeah, basically you can sign whatever you want with like any size. Yeah, that's the actual. That's what. So the Yubikey thing never saw the message at all. It only saw the the hash of the message, and hashing is pretty quick, I would say, and that can be done on the OS because there's nothing secret about the hashing. So when you talk to PKCS 11, if you read the interface expects the hash. Actually, it does not expect the blob. And you can do the whole hashing on the OS, which usually has a much stronger CPU, and then that's usually the more costly operation, I would say. So you can do all the hashing on the OS because it's I/O bound. Like you are doing a lot of I/O if you are signing something big, and then once you have the hash, send the hash to the PKCS 11 library, and that will get it signed. And then you'll be as fast as the device can do it. So this device can do 5 signatures per second, 4 maybe. I think it takes like 220 milliseconds to do a signature. And a fast device would do north of 10,000 per second or something like that, which is pretty good. If you want to check benchmarks on your CPU, there is an OpenSSL speed command that it has all sorts of arguments that you can see how much crypto you can do with your CPU. And all the new Intel CPUs, they have something called AES-NI, which are AES instructions inside the CPU itself. So you can offload most of the heavy lifting to the CPU without doing the whole math through the normal ways. That's a very significant gain for AES, but that's symmetric crypto. For asymmetric crypto, unfortunately, there is nothing in normal computers that would do offloading unless you buy an HSM. Like an HSM will offload like everything, including asymmetric crypto. That's one of the reasons they cost a lot of money. Yeah, so basically, we talk about like primitive operations like signatures and decryption. Those are great, but like unless you were like a software developer developing something, you most likely we're never going to use the primitive operations. And most of the times you build stuff on top of it. And so pretty much every authentication protocol that you always use based on keys, like they use those primitives. Like so everything is built on top of that. So OpenSSH, SSL, TLS, OpenVPN, the IPsec, and etc. Everything is built on top of these same primitives, like signing and decryption and etc. So I want this talk to be useful as well. So from now on, I'm going to talk about actual how to use this on our normal lives. Like, so I'm pretty sure that most of you here use OpenSSH. So that's a very common tool. It's everywhere. Finally, Microsoft adopted. So even now, the Windows 10 starting sometime around now, they are shipping with OpenSSH by default, both server and client, which is fantastic. And I would say they have like 90% plus adoption in the SSH world. So you can use those devices for that. Like OpenSSH has had PKCS 11 support for several years now. And with this slide, basically I show how that works. So if you use public key authentication. So basically, when you use public key authentication, you may be aware of the authorized keys file. Like you have this authorized keys file on the server that you put your public key there. And whenever you SSH with your private key, the server will just authenticate you with like no passwords at all, which is pretty cool. So let's see how that works in practice. So yeah. So there is this command here. There's several ways to retrieve your public key. So I actually have my public key here. But this is not the format that OpenSSH likes, so I would have to use a tool to convert. But you don't need to use the tool. You can read the key directly in the format that OpenSSH wants, which is this, which probably is very familiar. And you have SSH, RSA, and this is my public key. So if I try to SSH to my own laptop now, yeah, it's just prompting for a password because there's no key set up anywhere. So what I'm going to do now, I'll just redirect the output of this to my. So you guys all know this, right? .ssh, authorized keys. Like this is pretty standard. So basically what I'm doing here, like I'm reading my own certificate from my Yubikey device. Like this is the public key. And I'm storing it here. So now that's what I have here. Like nothing special about it. So if I try to SSH now.
Did you have something on the Yubikey called SSH?
Nope.
That -K?
You mean here?
Yeah, -K.
Oh, that's the format. the format of the key. Yeah, if I don't put a format, let's show you. I'll get this, which is not what OpenSSH wants. So yeah, the dash K is basically the format. Yeah. So which it's the same thing actually. It's just the base 64 is slightly different, and
It's the same certificate you can use for everything, right?
you can use for everything. Yes, it's the same. Yeah. Everything that supports RSA authentication will work with that. So now I have, I have my authorized keys on my authorized keys file, and then when I SSH, instead of prompting for the password, my client is prompting for my PIN, which 123 123 enter. Done. I mean, like no passwords or anything. And if I remove my USB thing from here, I would never be able to authenticate. Yeah. Let me just remove that before I forget. Yeah.
To look on that device to find that key versus looking somewhere else?
Sorry, say again.
How did it know that the key that it needed to log into this particular host was on your?
Oh yeah, the OpenSSH has a trick to do that. So the way OpenSSH works, the client sends to the server all public keys that it has. Okay, I have all these public keys here, and the server will respond in the handshake protocol. I like that one. Prove me that you have it, and it sends you a challenge, and then you have to sign the challenge with that private key, and then when you send the response back to the server authenticates you.
So the first step didn't need the private key, so we didn't need to enter the PIN. But then the second step, it set back and said, I want this one. And
Yes.
then it had to find
Yeah,
it.
let me show you this. Yeah, actually, if you do a -v, you can see that happening actually. Yeah, so if I scroll up here, let's see, this is the server host. Yeah, offering keys. So I only have one. If I have multiple ones, it would offer everything. I have all these 300 keys here. Like, do you like any one of those? And the server would respond, yeah, this is fine, but you have to prove me that you have it. And then it sends a challenge. That's normal challenge response authentication protocol, basically. And then once you authenticate, the next thing is the key derivation. That's where it generates the symmetric key. Because everything else from here is symmetric. So once I authenticate, so I'm in. So now I can remove it. So now it's on my hand. The session is still working. And because like the only part that we need the key pair is for the authentication and to generate the private key for the session. Everything else is symmetric crypto. Because asymmetric crypto is very, very expensive. Like, it's insanely expensive. And so you only use that to derive a key or to negotiate a key actually for the rest of the session. That's the same thing with SSL and TLS and etc. You only need the public key and the private key to do the handshake. Once that's done, everything else is symmetric crypto. So if I get out and I try again, it will ask for the password because there's no keys anymore.
So I noticed up there it says it's going to rekey after some number of blocks. Does that mean after that number of blocks you'd have to reinsert the device?
No, the rekeying is done using the previous key.
Oh,
Yeah, it's a key derivation thing. Yeah. Yeah, this is with OpenSSH. Like, you may have a protocol that you do the rekey using the key pair. Then yes, then you would need the device all the time. Yeah.
So going back to generating these keys, how is that little device generating us a random number that's acceptable? What is it using?
It has a pseudo random generator in the device itself. Yeah, it's a PRNG inside the device. So it's not actual entropy. Some devices actually have actual entropy. They have like microphones and some like ambient sensors like temperature and humidity, and they use everything to feed the entropy. So the Thales ones have that. It's usually like a microphone, a thermometer, and a humidity sensor, and etc. And they just combine everything to create entropy. So I think this device is just a PRNG, which is a pseudo random.
How would you trust it? Like, what would you do with this random? Would you trust it for banking?
Maybe. I think anything is better than having a private key in disk. Like, so if you start from there, yes, I would trust it compared to where I'm coming from. Yeah, if you compare that with like tamper evident devices and something more sophisticated, maybe no. So those devices, they run an application inside. It's a very small application which could be compromised. Yeah, so that's what I say. It's not impossible to to break in them, but you have to be skeptical at the same time. Like, it really depends on, how big deal you are in terms of like a security profile. So all the big ones, they are all FIPS compliant, which might tell you something or not, because you never know. Most of them, you never have access to the source code. So basically you have to trust the vendor, which is complicated. And but that's a very good point. Like, if you really have something really serious, I would definitely recommend like use key derivation in multiple devices from different vendors. But then things get really complex to implement, right? But that's definitely doable.
Since you opened the OpenSSH door, I'm assuming that one thing well applies here. Does this stack with SSH agent? Can I use it
Yes.
to authenticate remotely?
Yes, with a caveat. So if your physical device is configured to request the PIN every time that you need to use the private key, then no. Then the SSH agent would load the key and it would work in the first time. The second time it would fail. So if you have a key and you configure that, I only request the PIN every hour or every day, then yes, you can load the key on the agent and then it would work for the next 24 hours. Some TPMs, like, so the MacBook one, the new ones, this one that has a touch bar, it has one of these devices inside, like on board. That's called a security enclave. So, and that one has a fingerprint reader. So you can load that key on the agent, and every time that you want to use it, the macOS will prompt you for your finger. That's all done in hardware. The OS will never see that. The OS will just interface with the thing using their own libraries, and the library will just tell, okay, the fingerprint was good or not. And it's all done in hardware. So it really depends. Look, so different devices will have, it depends on how your authentication is done through the, so if you go to the SSH add command, which is the agent, right? You see the two lines here? PKCS 11? Yeah, basically that. You can load the PKCS 11 key to the agent, and then it works. But that all depends on the authentication that you have on the device itself. Going back here, so this is OpenSSH. 2 years ago when I was here, I was talking about SSH certificate authorities, where instead of using public keys, I was advocating for people to use certificates instead. And I still do that. And through the end of these slides, I'll show you a link of a blog post on our Facebook engineering blog, where I talk pretty much about what I talked 2 years ago here. And then you can combine this talk with the previous talk and make a good lemonade out of it. And so SSH Keychain, that's the tool that you use to create certificate. It also supports PKCS 11 providers. So that's exactly what this command does here. I'm not going to demo that because I don't have a CA. But if you have a CA, you can have your CA backed by one of these devices, and then you sign those certificates that way. And this is useful for small CAs, when you can have a human interaction to issue certificates. If you are issuing certificates programmatically, then it's a little bit more complicated because of the PIN. And so in Facebook we use HSMs for that, so it's like a whole different story. But fundamentally it's the same thing. Like, at some point our certificate authority is talking PKCS 11 to the HSM and gets the job done. OpenSSL, that's a lot more complicated because the way OpenSSL has been done. So if you never read the OpenSSL code, never do it, because it's depressing. And it is depressing for a good reason. Like, it's written to be performant. It's not written to be understandable. So it's very difficult, and it's a very old project. So this has been around for like decades now. So in the way, when they invented OpenSSL, they created this concept of key engines. So when you use OpenSSL, most of us, when you use OpenSSL, the default key engine is the file system. So we basically tell where the private key is on the file system, and the OpenSSL goes there and opens. But actually, this is implemented through an engine. So OpenSSL has an interface, like a PKCS 11 interface, but it's our internal interface, where you can create engines for that. So you can offload the private key operations to something else, whatever you want it to be. One of these engines is actually PKCS 11, which is not provided by OpenSSL itself. That's where we go back to OpenSSC. That's the other project that I had mentioned before. And so if you want to use OpenSSL with a PKCS 11 provider to talk to one of these devices, you have all these abstractions to go through. It works. The command line OpenSSL itself, it's just a wrapper actually. If you read that code, like that code is basically a wrapper around libSSL, which actually does the work. libSSL have its own engines, which we have like libp11, that's one of the OpenSSL libraries, and then talks to the PKCS 11 provider that talks to the device. It's like kind of annoying, but it works. And the configuration is a little bit annoying because you have to go through all these abstractions. And yeah, it's not supposed to be very understandable, but trust me, it works. And so yeah, let me go back here to my notes here. So yeah, so this is the config. So I'll just copy and paste here very quickly. Yeah, but yeah, that's my config. And so I have the OpenSSL that comes with Mac. So that does not have the libraries and include files. So I have another one that comes with brew. So I'm going to use that one. So I'm going to create that alias here. If you run on Linux, this is no big deal. It just works.
You installed with brew?
Brew install OpenSSL. Basically that. So it will just be in a different path. So if you want that to be your default, just change your path. And so what I'm going to do here is exactly what I did with PKCS 11.2, to sign a message. And but I'm going to do that through OpenSSL. So as I said, there is this digest command. So what I'm telling OpenSSL here is basically, instead of telling you where the private key is on disk, I'm telling you that I'm using an engine. So the format of the key is like the engine, it's kind of redundant. So I have to tell OpenSSL which slot to use, otherwise it will complain. So use slot 0. Hash the message with like SHA-256. As I said before, we don't sign messages, we sign hashes. And then output the signature to this file, and this is the message that I want to sign. Yeah, it's kind of complicated, but once you get it, yeah, yeah, the pin. Oops, 1, 2, 3, 1, 2, 3. It asks twice. I don't know why, but it does. And yeah, this is my signature. Now I can use OpenSSL to verify. So the verification command, I don't need to do PKCS 11 at all because the verification is done against the public key. Right? Yeah, verification, okay. So that's exactly what I did before, just using a different command, going through all those layers of abstractions and etc. So yeah, if you want to do small things, just use the PKCS 11.2. That's a lot easier. But if you want to do something programmatic, like OpenSSL exists, there is OpenSSL bindings for pretty much every language you can possibly imagine, like Python, C, whatever. And so it's very useful actually when you are using this programmatic, like let's say a Python or Go or something like that. And it's actually better to understand how this works because you're going to need it. The interesting thing about this whole config here, like this config is read by the library itself. It's not read by the OpenSSL command line. So if you are using OpenSSL via Perl or via Python, this will work as well. And because the library is reading that config and the library is reading all the providers and etc., which is pretty much what you want. Yeah, so this is what I did. Nothing special about it. Yeah, we don't have much time, so kind of wrap up in a few more slides. Let's see, I have a few more to go. And so yeah, just talk about security in general. So when you start using those devices, like you have to keep some goals and non-goals in mind. Like, so I think the main goal is to make it impossible to duplicate the private key. That's what you want when you are using this device. Like basically, there's no duplication. Some of these devices, not this small one, I think the bigger ones, they support secure logging. By secure logging, I'm talking about like blockchain logging. So like the next line is signed by the previous line and et cetera, et cetera. So like if you tamper with the log, that's evident. And so this is called like ledger, and there are some like banks use that, have been using that forever. And so those devices support that, and the signature is done in hardware, so there is no way to tamper with that. So the Thales HSM support that. So when every operation that I send to it, it logs like securely, and I can download those logs via an API, and I can use the public key that the device gives me to verify if the chain has not been compromised. So this is really important. Right? So tamper resistance, if you're using like an external appliance, that's something that it is a go for this kind of stuff. One thing that's not a go is key misuse. So if you get access to my device and my device has no PIN or you know the key, there's nothing that I can do to prevent you from misusing that key. And so that's something just to keep in mind. Like you might spend like lots of money on these HSMs and build like entire HSM infrastructure, and then if you're using this whole infrastructure in a programmatic way, that means that you can't be prompting for pings all the time because it's programmatic. And which also means that if someone compromises your application or your OS, they can't actually issue commands to the HSM to get stuff signed or decrypted programmatically, and there's nothing that you can do about this. So just be careful about, because that's not the problem that you were trying to solve when you have this kind of stuff. And but the worst case scenario, like if you protect your infrastructure again, you don't need to rotate the key because the key is protected again. Like if your key is in the file system and people copy that key, you have to revoke it because like you really don't know how many copies of that key exists like elsewhere. So you have to revoke it. That's the interesting thing. Like, so this allows you to have like much longer living certificates, like a couple more years instead of like months or so, because it's pretty much impossible that those keys would ever be compromised, would ever be copied. They could be misused, but not copied. So you may know this. So when you're dealing with like certificates, especially X509 certificates, that's the one that you use for HTTPS and pretty much everything these days. So we have this concept of chains. Most of like smaller companies, they don't use that, but it's something that we strongly suggest. So this is an example of like the certificate that we use at Facebook. We buy our certificates from DigiCert, and DigiCert has this root CA, which signs a certificate that's the intermediate CA, or they call server CA. And that intermediate actually signs Facebook. And the browsers, they have ways to verify the entire chain. The interesting thing about the root CA in those cases is that the root CA can be kept offline. And by offline, I mean in a safe, locked, like no power, no network, like nothing. And because the CAs, they are only used to sign the intermediates. And you only do that every couple of years or so. And that's how we do at Facebook. We have an offline CA. It's in a safe box, like super secure. It has like secret sharing. So whenever we want to use the root CA, we have to get the minimum number of people in a room, and then we can do some operations with that CA. Super secure. It has secure logging and etc. And that's what all the big CAs do as well. And the intermediate CAs, they cannot be offline because they are signing certificates all day long. So those can be online. And so they also use HSMs, but they use online HSMs. So those HSMs are connected in a network somewhere. And they always have shorter validity. This particular one is 10 years. At Facebook, we do 2 years. So it really depends. That's up to you. The very interesting thing here is that the root can revoke intermediates. So if your intermediate has been compromised, let's say that someone stole your HSM, like physically, and then so that means that they cannot copy the key from there, but they have the HSM in hand, so that's also a compromise. The root can revoke the intermediate, and then everything that intermediate signed gets revoked by side effect, which is really interesting. So the root, which is offline inside a safe, can just create a new intermediate, and then you don't need to redo the entire chain of trust. The root itself cannot be revoked, and that's the main reason that it has to be offline. Because if your root leaks, you are in big, big trouble. So I really suggest you reading about DigiNotar. This was a Dutch root CA that was compromised a couple of years ago. People start issuing certificates on their name, and they issued Google.com and some other like really important certificates. The main suspicion here was something coming from the Iranian government, but it was never proved. And it was a huge, huge, huge mess because all browsers in the world, they trusted that CA. And they took like several years to update all the trust stores across all browsers and OSs to not trust that CA. And it's quite possible that even today, there are devices, especially like Internet of Things device that never gets updated, which still trust DigiNotar. And that root CA has been compromised. So that's how big deal it is a root CA. So you really need to be super, super serious about it, because if it leaks, you were definitely in deep trouble. Yeah, you lose your private key. So when you need reliability, if it's a user device and you lose the device, I would say just create a new key and update the public keys. When in the CAs, the way we do it, we import the key into the certificate, into the device, which I said before that you shouldn't do it. The way that we did it, like we have like an offline laptop that we bought it off the shelf, like in a Best Buy or whatever. It's completely offline, has no network, nothing. And then we use that device to create the keys, and then we import the key in multiple tokens. That's how we did it. Some HSMs, they support rapid exports. The Thales supports that. That's what we use for our online HSMs. So you can tell the device, wrap that key and give the key back to me. And then you can, if you have all the devices on the same cloud, they call it security world. If you have devices on the same cloud, you can re-import that key in other devices. So the big ones, they do support that. The small ones, I would suggest you do with an offline laptop, create the key like in disk, import to several of them, and make sure that that key has never been written like anywhere, like a laptop without disk, without network. So our laptop has no network interfaces, no disks. We boot with a USB device. So all the commands that I used is here. So this is the URL. And I guess you're going to share these slides. I have to send you. Right? Yeah, we'll just take a picture of this QR code. And so this is... Oh, because it's very destructive. Because we will erase the device and it's every time that you run it, which is the same as losing the device. And so, yeah, don't run the script unless you want to destroy your device. And
I just lost my device.
oh, I'm sorry. If you like crypto, I really, really recommend this book. It's really nice. It's not a book for mathematicians. Like it talks pretty well about like cryptography and some ciphers and etc. But it's more for like humans to read it. And it's like very easygoing. I read the whole thing a few months ago. It's really, really nice to understand like the primitives of cryptography, like what's signing, what's decryption, what's verification and hashing and etc. What?
Can you switch back to that last video?
Yeah, go ahead. And it's a pretty interesting book. And the guy wrote pretty much for, I think the audience was more like sysadmins and yeah, people like me and you that like we use cryptography to solve business problems. We're not actually working on cryptography itself.
Quick question. Are you typically saving your management key?
Sorry, say again?
Your management key?
I have on my password manager. Yeah, that's where I save my own. Yeah.
Put it at a big company? You managing a ton?
Yeah, that's a very good question.
Can you restate it?
Hmm?
Can you restate it?
Yeah, where do we save the management key if we're deploying this in large scale? And so that's actually a very good question. And yeah, you have like a couple options here. Like if you want to have unique keys, you have to save this securely somehow in a directory or something that you can retrieve. Or you can use the same key for all the devices, which is... Yeah, it's really not a big deal. Like if that key leaks, because you can't use that key to do private key operations. You can only use that key to write to slots and to change the state of the device. So if you use the same key across all devices, I wouldn't say that's an actual security problem. Like people would never be able to impersonate our employees if they get their hands on the management key. They would be able to create another key in the device, which may or may not be bad, but they will never be able to use the actual keys that are in the device already. Because of the pin. You can't change the pin with the management key. You have to have the PUC. And
So to that, and if you write down the PUC and you can change the pin with the PUC,
yeah.
What's the difference between writing down the PUC and writing down the pin?
Yeah, no, yeah. The PUC is kind of, for me, it's kind of useless.
There's no difference, right?
Yeah, exactly. When I created my PUC, I use a random number generator, and I set the PUC, and I forget it. So if I lose my pin, I lost my device, basically. I'm fine with that. Like, it really depends on the business application. Like, if it's for user authentication, users lose things all the time. So you have to have a business process for that, because people are losing shit all the time. Like, there's nothing that you can do about it. And so you have to have a process for that anyways. So I wouldn't care about PUC. And I would just, like, throw the PUC away, basically. Just change it. Like, if you don't change the PUC in those Yubikey devices, your PUC will be 1, 2, 3, 4, 5, 6, 7, 8. So change it, because otherwise the device is very unprotected. So yeah, this is the book. Like Amazon, Serious Cryptography. There is a Kindle version. It costs like 10, 15 bucks. Definitely recommend it. Really, really good. So last time that I came here, I talked about SSH, as I said. So there is when I was here, actually, I was about to publish a blog post in the engineering blog. And that actually took like 2 more months to do it. And I think I told you when I did it, like, and you posted in the mailing list somewhere. Anyway, that post is still out there. That post is out. It does not talk about crypto device, but it focuses mostly around like SSH certificates. So if you combine this knowledge here with that knowledge there, you can use this stuff here to have an OpenSSH CA. We still have, I guess, 15 more minutes, right, for questions, and I'm happy to answer like anything. What? 5? Okay.
So this is admittedly an obscure kind of situation. So I'm trying to protect an environment that is like for experiments, and it's like Wild West, right?
Right.
And people are setting up servers, and it's not the standard set of
Right.
software.
Yeah.
We're just bringing
Right.
stuff in. So I'm wondering if this could be a solution for setting up a ring of trust, so a basis
Right.
for a ring of trust, so web
Okay.
browsers could hit these servers without really knowing what it is the server has.
What problem are you trying to solve? Like authenticate? What's your concern?
So right now, the web server, when you go to the web browser and hit one of these servers, it pops up saying, hey, you don't have a ring of trust. You don't have
Okay.
a CA,
Okay.
you can't set that up.
Okay.
And we can't set that up because
It's a lab.
It's just constantly changing.
It's just a lab, yeah. Yeah. So if you want, So in that case, you want to authenticate the machines, right? You could use that. I wouldn't say it's probably the best solution, but because you have to provision that somehow. So if you have a lab where people are like setting up all sorts of stuff, like, and you don't have a provisioning process, like there's no way for you to actually go there and configure this device, like set the keys and etc. So yeah, that's actually a very interesting problem. And we do have labs at Facebook, and it's a huge nightmare for us because of that. Like people are always setting up different things, so we have to sandbox them basically in the network. They only have internet access, and then okay, do whatever they want, but you don't talk to our production networks because it's basically Wild West. And unfortunately, I don't have a good answer. But if you have an ability to do provisioning, but if you have the ability, your problem is already solved anyways, like regardless of having a security device or not. It is doable, but you have to provision them somehow.
Okay.
Yeah. Yep.
What was that last slide?
This one?
Yeah.
Yeah.
What was that one about? Was that
That's the CA certificate
law
authority.
that's
Yeah.
Talk he gave 2 years ago.
Yeah.
Oh, I see.
Yeah. And I wrote a blog post about it, which is pretty much the same thing.
Okay.
And it has a lot of good
So
examples.
I mean, do you still people to talk about that out there?
Yeah. Yeah.
Okay.
Yeah. Yeah. I should probably do a second revision of that, including this PKCS 11 stuff. I think that would be pretty useful.
That's
And
2019.
2019. Yeah. Yeah. I'll give it the 2 talks combined. Yeah.
That blog post stands well on its own.
No, it stands really well. Yeah, really well. Yeah, if you just add to that instead of using private keys on disk, you use private keys backed by a PKCS 11 provider, everything is just up to date. That's how we run Facebook. Like we run with SSH certificates everywhere. Like, and that's how we do authentication. We just use like a mix of like private keys and on memory or private keys and backed by hardware device. It really depends on the situation.
So everything you were talking about was using that for clients.
Yes.
Could you secure a web server?
Yes, but the problem with the web server is that if you have one server, yes, you can definitely do that. And but what problem is actually that solving? Like if you have your physical device already like safe, like so the whole server is already secure, like what having a key inserted to the server would buy you? It still protects the private key, which is important. I would definitely do that. But most of the commercial implementations, like you have your SSL certificate in a load balancer, so you have to do that actually in the load balancer. If you have multiple load balancers, then you have a problem because you're gonna have to share the same private key across multiple load balancers. So yeah, all the big load balancers support that. If you buy an F5 or something like that, it supports that. In software, I'm pretty sure that HA proxy and all of those, they also support that because they are built on top of an OpenSSL. And I think it would be beneficial so that people would never be able to copy a private key. So they would never be able to steal your certificate.
But is that also performance?
Yes, that's a problem. You can't use those Yubikeys for that because then you can only do like 4 or 5 handshakes per second. But if you buy an HSM card, that's what people do in general. Yes, you can do that. You can tie, either with a PCI card or with an external HSM. Then you can do all your SSL handshakes on that. I would definitely recommend doing that. That's definitely not cheap. I think like it would start here at $10,000-$20,000 to get something like that done. Yeah, if you're really concerned about your certificate, like we are, and you have to do something like this. It would be very, very big trouble if our certificate leaked. So then we have to go like long ways to protect it. Questions? We still have time. I don't know. So I'm coming to the dinner. So if you are coming as well, I'm very happy to chat. And thanks very much. Thanks so much for stopping by, and it's again a pleasure to come here. So before I forget, get your thing back.